So let's start with the first of those AIs, SiD, that we have developed. It's about selecting single spermatozoa during the ICSI process. And it's an important moment, and it's underappreciated, really, how that is done. In conventional ICSI, when you look through a scope, or when you have a camera on the scope and you look at the display, at the monitor, you have difficulties tracking multiple sperms simultaneously. That's where the human eye is not that helpful. A monitor that's making a video actually has all the pixels, millions of them in sequence, and does that instantaneously. Our eyes are, or our ability to interpret what we see is not that straightforward. So we can track a few spermatozoa, but we can't track 100 and do that within a few minutes. And even if we track 100, we would lose their positions because all those pathways overlap. And you can only do that for about 5 or 6 sperm, keeping track of this previous sperm that you have just scored. So what we do as embryologists, and I would do it too, you dilute the sperm sample so you only see a few sperm. But that, of course, reduces your selection power. That means that you're actually not selecting sperms that well. And so that's what we try to solve with SiD. So the question can be asked, do we really select? In most instances, it's a very immediate selection between maybe 2 or 3 spermatozoa. Are there studies about this, how embryologists select sperm? I haven't come across one yet, but I've maybe missed it. But I don't know of any studies that we show selection and how it should be done. And of course, we do know that there are differences between staff and outcomes. And that is the same for embryologists that perform ICSI and ICSI outcomes. How many blasts do we get? What's the fertilization rate? What are the long-term outcomes? So could the sperm selection process be related to that? So here you see a short video how we normally in the lab do sperm selection. There are variations on what you just saw, but how are you going to select the sperm at that level? So when you do SiD and you move the micro tool where you're going to put the sperm into the middle, this is the interface. It activates SiD, and it will look at all the pixels and score all the spermatozoa that are there and looks at their motility patterns. So here's a different magnification where you see things a little better. As you see the ranking that comes up, and all you need is to bring your needle forward to the sperm tail and immobilize that in whatever way you do that. Most of the time that's done either with piezo or it's done with mechanical, with the needle sticking the tail. The 2 questions we can ask in developing the SiD AI, the questions we certainly ask, is there an association between individual motility patterns of single spermatozoa that are selected by the embryologist for ICSI or not selected by the embryologist? Both questions are important, or both alternatives are important. And secondly, can a score based on such findings be used to pinpoint spermatozoa that may be selected for ICSI on purpose? And so those are the questions we asked when we developed this about 5 years ago. When we select the sperm with this AI, using the method that I've shown you in that short video, one unpublished study, which unfortunately not published but never reached statistical significance, showed that it increased euploidy rates in a program that does both PGTA as well as SiD. But 2 publications that were presented at meetings about 2-3 years ago showed that if you take an aspiring embryologist, a junior embryologist, a trainee embryologist that is just starting to do ICSI and compare them to senior embryologists who have a lot of experience with ICSI, it shows that the outcomes were equivalent. Outcomes in this case means fertilization rates were the same and blastocyst formation rates. Usable blastocyst formation rate was the same. Another study done, this one was published and was done in Toronto by Debbie Monjan and others in a program in Canada. They showed that when they looked at the euploidy rate in their lab, that when they performed ICSI, and you can see that here on the bottom of the screen, 53% of embryos of blastocyst were euploid, whereas if they did regular ICSI, so that was with SiD, when they did regular ICSI, it was 44%. And the cumulative clinical pregnancy rate was 27% when they used SiD and 21% when they did ICSI. That was not significant. None of these comparisons were significant, but they all had trends. And also the fertilization rate that are presented in the same paper, there was clearly a trend to improvement, but they just didn't have enough numbers to show significance. So we wanted, from the early days on, we knew that there was a restriction in the way we had developed this. We had developed this with one lab in Guadalajara, Mexico, and used their data on motility with a fixed feature set to develop the first version. In developing the second version, which was developed over the last 2 years, the data set, or the feature set, I should say, was fourfold in comparison to the first version. And we only used data from one clinic to develop the first version. In the second version, we developed it with data from 6 clinics. And when I say data, what it means is you videotape the selected sperm for ICSI in each of the oocytes, and then you culture them separately, and you follow those through fertilization, and you follow those through blastocyst. And if you can, you follow those to pregnancy. So now you can go from a single sperm all the way with data to the blastocyst and pregnancy. And so this is an enormous effort that was put into this. So the outcomes from single spermatozoa, and you can see that here in the third row, 3,000 spermatozoa were used, single spermatozoa were used in the first development of the first core, but it was over 20,000 sperm cells which were used from the diverse populations from the 6 clinics which were used to develop the second core. So the first core was algorithmic. In its true sense, a mathematician would have said it's algorithmic and it's not really a true AI. The second one is generative and is an AI. It's AI-powered with a data-centric model. And also a big difference, or users think it's a big difference. The first one did not have morphology evaluation of the moving spermatozoa. It is not so simple to get morphology evaluations of moving spermatozoa. It can be done, but it is costly in terms of engineering. It's costly, but it's also costly because you're using a lot of CPU or GPU power. So it's kind of expensive and polluting because your computers have to be very big locally. And so certainly doing it over the internet would slow things down. The second version, we have developed morphology screening, but only on notable defects. If the sperm goes around in circles because it's very asymmetric, when it has 2 tails, when it has 2 heads, those are the notable defects that we pick up. Can we pick up smaller defects as well? Yes, but that takes us into a different level of computing, and we like to stay away from that. But we are developing an alternative version that can do that too for labs that really, really want it. I personally feel that the association or correlation between morphology of the sperm and its motility is very high, and that you really do not need the morphology at that level. And in actual fact, most clinics nowadays use strict criteria to do their morphology screening in a sperm population, not in single spermatozoa, but in a sperm population. And they find that it's not that helpful. And I think the same applies when you go to the single sperm level. So the interface of this second model is different. And I'll show you a videotape soon. It's trained on 20,000 single spermatozoa, as I said, from 6 clinics. It has an 80% accuracy model. It uses blastocyst formation as outcome. The home screen can be used for procedure tracking. You have preferences. It's a totally different program. And you get cloud video synchronization, but the videos can also be stored or stored locally on your computer as well. So this is the second interface. It's more quiet than the first one that you saw, because the ones that are excluded, for instance, bad morphology, is the ones that you see on the top. There are two that have very bad morphology. Those are excluded. They are basically not targeted at all for further analysis. So it's a bit more quiet way of showing the interface. There are downloadable reports. So, for instance, you see in this graph on the right, in the blue line in the middle of that report, you see that most of the spermatozoa in that particular sample that was tested gave a score of over 70%. And the score is going up to 100%. It goes from 0 to 100. It's the same for Erica, and I'll come to that shortly. And so in this particular case, the sperm that was picked, the system will track. And if you individually culture those zygotes, you could then correlate it with your other KPIs to look at fertilization and blastocyst formation. And the score of that particular sperm was 80.67. And so this is how that is done. It gives you very different information than you had before. You have personal preferences. And this is an early outcome. The blue bars show SiD version 2. And in this particular study, that didn't improve the fertilization rate, which is the left columns, the left bar graph. And the second bar graph, which shows blastocyst utilization of 50% or better, those are the blastocyst utilization rates from SiD version 1 in pink. In green, it's SiD version 1 scored by the Canadian group, which is very similar to the one that was obtained in Guadalajara, Mexico. And then SiD version 2 is the blue bar, which is a significant improvement in blastocyst formation rate. But this is just one study. A second study that needs to be published still, and it's just been submitted for publication, was a sibling oocyte study, similar to the study that actually was performed in Canada. And that shows an improved fertilization rate. The Canadian program did not show that. They showed improved blastocyst rate. This particular study done in Guadalajara showed improved fertilization rate in a sibling oocyte study, from 83% in the control group, which is pretty high after ICSI, to 10% more when SiD version 2 was used to select the spermatozoa, with a pretty high significance level. But it didn't show blastocyst formation rate significantly being improved, although there is a small trend there. Of course, when your control groups are very high, you need a lot of numbers to get better than that. So what SiD has shown, it's an AI that's always is optional. All AIs are, you can just ignore them. It's an assistant. You can agree or disagree, you can ignore it. But it does give you greater confidence over time. At least that's the feedback we get from embryologists using it. In at least 2 studies, there was equivalent between experienced and inexperienced embryologists. And so that's an interesting thing. So it probably teaches inexperienced embryologists over time much faster than they would be taught if they did this without supervision, where they themselves have to find out what the best sperm is to select. What we know from all the data so far, that SiD is at least as good as an embryologist. I think that's important. Of course, people say, but it's not better than an embryologist, but that's what we want. Yeah, I think we'll get there. But right now, I think there's little doubt that it is as good as an embryologist.